Hey everyone, sorry about the mix-up with class on Wednesday. Today, our class online will be finishing up our lecture notes from last week. We are a little bit behind on the schedule, which is fine, but just to mention, when we return, we will work on chapters 5, which is applications of all of what we're doing, and our exam will remain in the same place the Monday after not the Monday we come back from break, but the following Monday, as it is in the schedule. I've updated the homework problems in Canvas, so if you have any confusion about what is due, again, don't worry about the schedule, just follow whatever is posted on Canvas. But basically, your homework from chapter 4 is what is due when we come back. And 4142 is optional. It says in Canvas as well. So anyways, I know I've told you guys some of this stuff already, but just to be clear, you can always double check in Canvas if you have any issues. So let's continue where we left off on Monday, which is on derivatives involving exponentials and logarithmic functions. So far we've talked about the derivative of the natural log function, which is 1 over x. And we also know the derivative of the natural exponential function, e to the x, is also e to the x. However, when we change the base of an exponential to any base, it was a little bit different. And I wanted to show you guys another way of sort of verifying this property that the derivative of any base exponential function is the natural log of a times the function a to the x power. And you can actually do it using the chain rule and using some properties of the logarithmic function itself. You know, now that we've talked more about the logarithm and a lot of its properties, but a mathematical property of the logarithm, sorry, I'm trying to find the right page on my tablet. There we go. Now I should be able to write on screen. Okay, looks good. But is the property that if we compose an exponential function with a logarithmic function, they cancel it out. So we refer to these properties as the cancellation properties. Let me just write them below. But one example is if we were to take the logarithm base a of a to the x, what that always leaves us with is x, because again, the logic is that if a logarithm helps us to figure out, okay, a to what power makes the input, and the answer to that equation is x. But for me, I think that there's a much simpler way to remembering this, is that when I compose a logarithm and an exponential, basically log base a and base a to the x power, those are opposites. They cancel out, much like because they're mathematical inverses by literal definition. The definition of a logarithm is there to be the opposite of an exponential, to help us solve exponential equations, and it's why they cancel. It's kind of like how, if you ever wonder, well, why does a square root and a square cancel like that? Same exact reason, because squaring and square rooting is mathematical opposite, just like plus and minus or multiplying and dividing when we're solving an equation, right? They cancel because they do the opposite thing. But if we compose them in the opposite order, if I have a raised to the log base a of x power, those also cancel and produce x for the same reason. In essentially, again, you can always make sense of this by changing it into a logarithmic equation, because remember, an exponential, if I think about this as a to the y equal x, we could change this to log base a of x is equal to y by the definition of log. And what we see is that, of course, log base a of x is equal to log base a of x, and I'm trying to provide reasoning on why this makes sense. Anyways, why do you care about any of this? Why is this relevant? Well, I just wanted to show you another tactic. It's an algebraic tactic which is useful in math sometimes. And it's another way of thinking about the derivative of exponentials and logs using this sort of compositional idea. But so let's, for example, say that we're dealing with the function a of x and we wanted to know its derivative. I could rewrite this function f of x as equal to e raised to the ln a power of x instead. And in your guys' notes, the a, I think for some reason there was a graphical glitch and it did not print out, but there's a little gap there and there should be an a there. So I might be wrong. Maybe it did print out properly, but in my notes, for some reason, it was written as a blank. I have no idea why. But I have a bunch of writing on here. I can't actually erase it, but that's okay. But if you're like, okay, if you're trying to make sense of what the heck this is going on here, well, essentially we have e raised to the ln of ax. And remember, e and ln cancel each other out because they're inverses, e raised to the ln specifically. And what that would leave us with is simply a to the x power. So this is equal to a to the x. But essentially what we're trying to do is, if we want to know what is f prime, we could start by taking the derivative of e to the ln ax. And again, the natural log of a raised to the x power is what we're dealing with. And this would help us to figure out what's the derivative of the generic-based exponential function. And if you're wondering, okay, how the heck would I find this derivative? Well, first of all, we could use the log law number 3, which says that if we have an exponent within a logarithm, that's always equal to that exponent multiplied by the logarithm. And notice that, what I have going on here in the exponent is ln of a raised to the x power. I could drop this x power in front. I wouldn't go through the exponential, but it would just go directly in front of the logarithm. So this would be equal to e raised to the x ln a power. Let me kind of get that out of the way, by rule for logarithm. So essentially, summary, if you have an exponent within a logarithm, you can pull it out front as a multiplier. And the reason why this, if you're wondering where to go from here, well, we could easily solve the derivative of this using the chain rule, because we already know, well, the derivative of e to the x is e to the x. And so if I want to change, what I have on the input, I could take the derivative of the exterior function, which I'll go ahead and highlight that in blue. Again, thinking about it as inside and outside, as well, take the derivative of the outside, which is just e to the same thing, leave the inside alone, but we need to multiply by the derivative of the inside. And basically, well, the derivative of the inside, since it's just x times ln a, well, we know the derivative of x is 1, and the derivative of a coefficient will not affect the derivative. So if we take the coefficient multiplied by 1, this would just give us the natural log of a as the derivative of x ln a. And if I lost you there, think about 3x, right? If I want to find the derivative of 3x, that's just 3. It's the slope. A linear function has a straight slope equal to its coefficient. And this is just x times ln a, and ln a is just some numerical value. It's the natural log of the base. Whatever the base is, a is not. It's not a variable. We're treating this as just a number that we know. But anyways, because I don't need the product rule to find the derivative of that, because it's just, derivative of x is just 1, and ln a is just a constant. But essentially, what we'd end up with is this e x ln a, e raised to the x ln a times ln a as our derivative. And notice, the whole point of my justification here is this is where the ln a comes from. And if we're looking at e x ln a, that's just equal to e to the ln a of x. Again, if we were to reverse the log law number 3 and put that, put that x back into the exponent like that, then we would have, well, I could move this back, and well, again, e and ln, we could cancel those out. So what we'd end up with is a to the x multiplied by ln of a. But this is just another way of remembering or thinking about the derivative of a to the x by applying the chain rule and laws for logarithms. And I think it's kind of an interesting demonstration that, okay, this rule works in other contexts as well. If you wanted to use the chain rule, it still would hold and give us the same general property. And notice we didn't have to use limits. If you remember how I justified this to you guys before, we did this by using the difference quotient. And at the time, I was just sort of like, believe me that this limit is the natural log of a. But we can see this makes sense a lot more clearly now that we know how logarithms work, at the end of the day. And to me, why this is so easy to remember is I'm kind of thinking about this as sort of like the derivative of the inside by the chain rule. The derivative is the same thing, but I'm multiplying by ln of a. It doesn't exactly make sense because it's a little bit more complicated than just the chain rule only. There's also some algebra involved, but the ln of the base makes some sense because it's an exponential function, base a, and that's ln a is, the natural log of e. I don't know. It sort of makes sense to me, and that's one way of memorizing that formula. So anyways, in the next video, we'll talk about what's the derivative of a general log-based function and how would we approach that. It turns out that we can do that quite simply using implicit differentiation, similar to how we did it using the common log Or you could even do it using the change of base formula, but we'll do it a couple different ways in the next